Hi, I'm Dr. James Wootton of the Decodoku project, and today we're going to be talking about the Bravyi-Haah method for quantum error correction. It was introduced by Bravyi and Haah in this paper, Analytic and Numerical Demonstration of Quantum Self-Correction in the 3D Cubic Code. Now, you might not understand that title, but you can maybe see that it doesn't say anything about introducing a new method for quantum error correction, because indeed it was about something else, and they just introduced a new method for quantum error correction as an aside, in an appendix. You can tell someone is a great physicist when their appendices are worth more than your papers. It puts me in mind of the recent Buckley Prize winner, Alexei Kitaev, who in one of his seminal papers, he was doubtless one of the ones that went towards his Buckley Prize, which is a prestigious prize in condensed matter theory. He has this section, odds and ends, which just has a few little asides, a few little comments that he's making. People have made multiple papers out of these comments. People have founded their careers on these comments. If you had a career in which you came up with these 9 things, you would probably win a prize or two yourself. But for Kitaev, they're just odds and ends. Anyway, this is not about Kitaev. This is about another equally brilliant Russian by the name of Bravyi, and also a Korean by the name of Haah, and the great method that they introduced. Now, I should say that if you ask Bravyi and Haah how they came up with the method, and indeed I did, they say that it was based on the method in James Harrington's PhD thesis. So you can check a link on the screen now if you want to check that out, but we're going to just be talking about the Bravyi-Haah method in this video. I should also say that I asked Bravyi and Haah a few questions about their method and what I should tell you about it, and they gave me some material which I'll keep on referring to throughout this video. So whenever I say something very wise or insightful, that is their material that I'm telling you. Whenever I say something stupid, that is pure Wootton gold. Right, now we're going to see how this algorithm works, and we're going to do that using Decodoku puzzles, which I've hacked slightly to be a little bit easier than normal, to give a more pedagogical view of how this algorithm works. To describe how this algorithm works, first we should remind ourselves what's actually going on here. This is a quantum error correcting code. It means that we've got a bunch of particles. These little things are particles. When errors happen on them, a signature arises in terms of these numbers that we measure. So a little error probably happened there, creating this 6 and a 4, and an error probably happened there, creating that 7 and a 3, and so on. Now in this particular code, these numbers will always add up to a multiple of 10. Now one of the great things about the Bravyi-Haah method is it can be applied to a wide variety of codes, not just this one where we get numbers which add up to a multiple of 10, but other crazy ones like the 3D cubic code where we get pyramids and stuff. The important thing is that when an error happens, we should be able to sensibly say that it creates some mess near it, and then we should be able to say that we can take that mess and move it all together and get rid of it by acting near it. For example, in this case we can get rid of the 6 and the 4 just by moving this 6 there, so we're just acting near the 6 and the 4. It's this principle of locality that seems kind of sensible, which we need for this algorithm. If we have a crazy code in which we do an error over there and it turns up over here, then that's not something that we're going to easily be able to apply Bravyi-Haah to. So now let's actually apply it. I think I've said let's actually apply it before, but I didn't. But now we're actually going to actually apply it. What we do firstly is look for connected clusters. So we look for groups of numbers which are all touching each other. For example, there's 7, 3, 7 and 3 form this little island here where the 7 touches the 3 touches the 7 touches the 3, and back round again, but that isn't necessary. Also we have this connected cluster all the way here which touches the question mark. We have this little one here, we have this one over here, we have this 5 on its own, and then we have the 7 with the question mark. Now we have to ask ourselves, do these things add up to a multiple of 10 or not? And if they've got a question mark in, we assume that they kind of do add up to a multiple of 10. And if they do add up to a multiple of 10, we also assume that they do, but if they don't, they don't. So here they add up to 20, which is a multiple of 10. Here they add up to 10, again a multiple of 10. Here we've got 10, add 5, but also a question mark, so we'll call that 10 as well. Here we've got 9, add 3, which is 12, add 7, which is 19, add 5, which is 24, and 24 is not a multiple of 10, and of course 5 on its own isn't either. So for everything that is a multiple of 10, what we do is we call that a cluster. We say, okay, these guys were created by the same set of errors. Let us act locally to get rid of them. So let's just pull those into each other. That's them gone. Let's move that there. That's that gone. Let's shove that there. And let's also shove that there. Okay, round 1 done. Now we're left with some stuff. We obviously have to do something else. If we're left with stuff, what we do is look at connected clusters where things are either next to each other or next to each other. So these are next to each other. They are just one step away, and these are 2 steps away. So we'll look at things that are just 1 step away or that they're 2 steps away, and we find that we have a connected cluster here where we've got this 5 and the 5, the 7 and the 3, and the 9, but also the question mark is 2 steps away, so we have to include that in the connected cluster as well. So we don't have to look at that if that adds up to a multiple of 10 or not, because it's got the question mark in. We move it all together and we win. What we find is that question mark and this one down here and that one over there were all a group. This one was a group, this one was a group. Crazy stuff was going on over here, but the Bravyi-Haah method meant that we didn't make any big mistakes and we brought them all together, which is fine in the end. And we were right about these, and we were right about these and these and these and this as well. So we done good. Now let's see what happens in our second version. We have this huge connected cluster here, which adds up to 10, 10, 10, 10, 10, 10, 10. So yep, that's a multiple of 10. This is also a multiple of 10, and this is a question mark. So let's just implement that. Boing, boing. Why am I saying boing? Nothing's bouncing. And then we have this 5 and a 5, which are 2 steps from each other, far away from everything else, so we can just bring them together, and again, we win. So Bravyi-Haah has this wonderful flexibility. It can be applied to so many problems. But what's the catch? What's the price we have to pay for that? Well, the price we have to pay is that it's got a relatively low threshold. That means the amount of noise that we can have before Bravyi-Haah starts giving us ludicrously stupid results is not that high. And we can see the kind of places that it goes wrong by looking at this example here, which I'm going to do in a spreadsheet for, well, I've got reasons, don't worry about that. So here we see a connected cluster. It adds up to a multiple of 10, 10 itself in fact, so we can get rid of those bad boys. And the same down here, and then we're out of connected clusters that add up to a multiple of 10. But if we look at things that are a distance 2 away from other ones, then we get this connected cluster which adds up to 20. So now we can get rid of all of those. I don't even know what happened there. So we can get rid of these guys. I'm putting dots just so we can remember where we were. And then we have this 9 and a 1, and the distance they are from each other is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And the distance from a question mark is only 7. So probably we're going to choose randomly one of these question marks. Let's go for that one. Add that 1 to it. 1 is not equal to 2. That's the basic mathematical result, which I've just used there. We're going to add this 9 over here. And that's going to be our result. We're going to think that we have to add these numbers down there, but it's not a good result. And it's not a good result because if we go back to what the original problem here was, we can see that pretty much everything's happening on this line across, and nothing's happening anywhere near the question marks. So it's much more sensible to say, well, maybe this 7 and the 3 are completely on their own. And then this pair of 1 and 9s are their own little cluster. Let's get rid of those. And this pair of 1 and 9s are their own little cluster. Let's get rid of those. That's what we would maybe do when looking at this as a human. But the Bravyi-Haah algorithm doesn't do this. The Bravyi-Haah algorithm is greedy. It looks at these, it sees them to be a cluster, it gets rid of them, but in its eagerness, it has made a mistake, and that mistake is going to be carried forward and is going to do bad things. So Bravyi-Haah has its weaknesses, and this is a particular example of them. So Bravyi-Haah just said to me that the weakness was a low threshold. This particular example of how to screw it up was actually due to Andrew Landau. He did some analysis of a similar method, the expanding diamonds method, which has the same weakness, and he found a number in that, and coupled with his healthy obsession with fractals, he realized that that number was related to the Cantor set, and that showed him a lot of in-depth knowledge about the kind of situations that can destroy these algorithms, which I have drawn upon in creating this particular example. This example is actually from the survey that we have for Decodoku puzzles that you can fill in to give us insights about your method and how it's better than Bravyi-Haah. Now let's just have a look at the email I got from Bravyi and Haah to say what I should say about their method. Dear James, I really enjoyed reading your Decodoku webpage. It's a very nice and elementary introduction to quantum computing and error correction. Blah 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 blah. Okay, so the only thing left was his great review of my website. You should really check it out. It's cool. Although of course I would say that, but someone who didn't need to say that was Sergey Bravyi, and he heaped praise upon it. I am a little bit proud about that. That's why I'm bragging. Okay, this was the Bravyi-Haah method. Thank you to Bravyi and Haah for helping me do this video. Thank you for watching. Thank you for listening. Thank you to my mother for birthing me. Thank you to makers of tea for making tea. Thank you to Star Trek for inspiring me. Thank you to Nintendo for inspiring me to make games. Thank you to Shigeru Miyamoto for making the best games that there ever were. I'm getting a bit carried away with the thank yous. You'd think it was me that won the Nobel Prize for topological stuff. You'd think it was me that won the prize that Kataev just won. But actually it wasn't. I am just going a bit mad.